From the dawn of civilization, humans have gazed at the cosmos in awe. The night sky, with its twinkling stars and mysterious planets, has always been a source of wonder and inspiration. We've pondered our place in the grand tapestry of existence. Philosophers and thinkers throughout history have sought to understand the universe and our role within it. The universe, in all its vastness and mystery, has always beckoned us to unravel its secrets. Its infinite expanse challenges our imagination and drives our quest for knowledge. Could there be a single, elegant theory that unlocks the universe's deepest mysteries? Scientists have long dreamed of finding a unifying principle that ties together all the forces of nature. A theory that explains everything from the smallest subatomic particles to the largest cosmic structures. Such a theory would provide a comprehensive understanding of the universe's fundamental workings. This is the audacious goal of the theory of everything, a hypothetical framework that would unify all the fundamental forces of nature. It aims to bridge the gap between the known and the unknown. For centuries, physicists have chipped away at the universe's enigmatic facade, revealing the laws that govern its behavior. Their relentless pursuit has led to remarkable discoveries. Isaac Newton gave us the laws of motion and gravity, illuminating the celestial dance of planets and stars. His work laid the foundation for classical mechanics. James Clerk Maxwell unified electricity and magnetism, paving the way for our modern technological age. His equations described the behavior of electromagnetic fields. Each breakthrough brought us closer to understanding the universe's intricate workings. These discoveries have expanded our knowledge and opened new avenues of exploration. But the quest for a unified theory, a single framework that encompasses all of nature's forces, remained elusive. Despite significant progress, the ultimate goal has yet to be achieved. This pursuit is not merely an academic exercise. It represents a fundamental human desire to comprehend the world around us and to find meaning in our existence. It strikes at the very heart of what it means to understand our place in the universe. By seeking a unified theory, we aim to answer some of the most profound questions about our reality. If we can comprehend the fundamental laws that govern reality, we gain a profound insight into the nature of existence itself. This knowledge could transform our understanding of the cosmos. The theory of everything, if it exists, holds the key to unlocking some of the universe's most enduring mysteries. It promises to reveal the underlying principles that shape our world. The search for this ultimate theory has captivated some of the brightest minds in history, leading to groundbreaking discoveries and revolutionizing our understanding of the cosmos. Their contributions have been invaluable, yet the path to unification has been fraught with challenges, forcing physicists to confront the limits of our current knowledge and to venture into uncharted territories of theoretical exploration. The journey continues, driven by curiosity and the relentless pursuit of truth. Albert Einstein, perhaps the most iconic figure in modern physics, dedicated much of his later life to the pursuit of a unified field theory. This theory aimed to combine the fundamental forces of nature into a single, all-encompassing framework. He sought to unite his own theory of general relativity, which describes gravity as the curvature of space-time, with the burgeoning field of quantum mechanics. This new field was revolutionizing our understanding of the microscopic world. Quantum mechanics, in stark contrast to the smooth, deterministic world of general relativity, revealed a universe governed by chance and uncertainty at the subatomic level. Particles behaved in ways that defied classical intuition, existing in multiple states simultaneously until observed. Einstein's quest for unification was driven by a deep-seated belief in the harmony and elegance of the universe. He envisioned a cosmos where all forces were manifestations of a single underlying principle. He famously remarked, "God does not play dice with the universe." This statement encapsulated his discomfort with the inherent randomness of quantum mechanics. Yet, the more physicists delved into the quantum realm, the more they realized that randomness and uncertainty were not merely artifacts of our limited understanding but fundamental aspects of reality. These principles were essential to the very fabric of the quantum world. The universe, it seemed, was not as neat and predictable as Einstein had hoped. The elegant equations of general relativity clashed with the probabilistic nature of quantum mechanics. The conflict between general relativity and quantum mechanics presented a major obstacle in the search for a theory of everything. This theory would need to reconcile the smooth, continuous nature of space-time with the discrete, probabilistic behavior of quantum particles. General relativity excels at describing the large-scale structure of the universe. explaining the behavior of planets, stars, and galaxies. It provides a comprehensive framework for understanding gravitational interactions on a cosmic scale. Quantum mechanics, on the other hand, reigns supreme in the microscopic realm, governing the interactions of atoms and subatomic particles. It has been instrumental in the development of technologies like semiconductors and lasers. These two pillars of modern physics, though incredibly successful in their respective domains, seemed fundamentally incompatible. The smooth curves of space-time described by relativity did not mesh with the jittery, probabilistic nature of quantum mechanics. Unifying these disparate worlds proved to be a formidable challenge. Physicists grappled with complex mathematical equations and theoretical models seeking a common ground. Attempts to incorporate gravity into the framework of quantum mechanics led to nonsensical infinities, suggesting a fundamental incompatibility between these two fundamental forces. These infinities indicated that our current understanding was incomplete. The universe, it seemed, was reluctant to reveal its deepest secrets so easily. Each discovery led to new questions, and the quest for a unified theory continued. The search for a theory of everything would require a radical new approach, a paradigm shift that could bridge the chasm between the macroscopic and the microscopic, between gravity and the quantum world. This quest remains one of the most profound challenges in modern physics, driving researchers to explore new frontiers and rethink the very foundations of our understanding of the universe. In the 1980s, a revolutionary idea emerged from the world of theoretical physics: string theory. This groundbreaking concept began to reshape our understanding of the universe at its most fundamental level. This theory proposed that the fundamental building blocks of the universe were not point-like particles as previously thought, but tiny vibrating strings. These strings, though incredibly small, held the potential to unlock the mysteries of the cosmos. Imagine these strings as minuscule, one-dimensional filaments, far smaller than anything we can currently observe. They are so tiny that even our most powerful microscopes cannot detect them directly. Just as a violin string can produce a variety of notes depending on its vibration, these fundamental strings, vibrating at different frequencies, give rise to the diverse array of particles we observe in nature. Each vibration pattern corresponds to a different particle, much like musical notes. Electrons, quarks, photons, all particles according to string theory, are simply different manifestations of these vibrating strings. This elegant idea unified the seemingly disparate particles into a single framework. This elegant concept offered a tantalizing glimpse of a universe woven from the music of these fundamental vibrations. It suggested that the universe itself could be seen as a grand cosmic symphony. String theory's allure extended beyond its aesthetic appeal. It promised to bridge the gap between the two pillars of modern physics. It offered a potential solution to the long-standing conflict between general relativity and quantum mechanics. These two theories, while incredibly successful in their own realms, had been notoriously difficult to reconcile. The mathematics of string theory naturally incorporated gravity, suggesting that it could be the elusive quantum theory of gravity that physicists had been seeking. This was a monumental step forward in the quest for a unified theory. This breakthrough sparked a wave of excitement in the physics community. Researchers from around the world began to explore the implications of this new theory. Could string theory be the long-sought theory of everything, the holy grail of modern physics? This question ignited passionate debates and inspired countless research papers. Despite its promise, string theory faced significant challenges. The mathematical complexity of the theory was daunting, and experimental verification seemed out of reach. For one, it required the existence of extra spatial dimensions beyond the familiar 3 dimensions of space and 1 dimension of time we experience. These additional dimensions were not something we could easily perceive. These extra dimensions, curled up and hidden from view at incredibly small scales, were necessary for the mathematical consistency of the theory. They provided the framework within which the strings could vibrate in the required ways. The idea of a universe with more than 4 dimensions might seem like something out of science fiction, but it was a natural consequence of string theory's elegant framework. This expanded view of the universe opened up new possibilities and challenges for physicists to explore. In order to address certain theoretical issues within string theory, physicists introduced a new concept: supersymmetry. This theory proposed a fundamental symmetry in nature between two basic types of particles, bosons and fermions. Bosons, such as photons and gluons, are force-carrying particles, while fermions, such as electrons and quarks, make up the matter we observe. Supersymmetry, often shortened to SUSY, posited that for every known boson there exists a corresponding fermionic partner, and vice versa. These hypothetical partner particles, with names like selectrons, squarks, and photinos, have yet to be observed experimentally. However, their existence is crucial for the mathematical consistency of many string theory models. The search for supersymmetric particles has become a major focus of experimental particle physics. At powerful accelerators like the Large Hadron Collider, scientists smash protons together at near light speeds, hoping to blast these elusive particles into existence. The discovery of supersymmetry would be a major breakthrough, providing strong evidence for string theory and offering a deeper understanding of the universe's fundamental symmetries. However, despite decades of searching, no conclusive evidence for supersymmetric particles has been found. The Large Hadron Collider, despite its unprecedented energy levels, has yet to detect any signs of these hypothetical particles. This lack of experimental verification has cast a shadow of doubt over supersymmetry and, by extension, some string theory models. The absence of supersymmetric particles raises questions about the validity of these theories and presents a significant challenge to our current understanding of particle physics.